Okay, fine. Everybody, good morning. Thanks for being here. So I'll be talking about some ideas on online learning for characterizing a no environment. So this is mostly the work of Alejandro, Jonathan Fink, Aaron and Ethan Stamp. Some of them are Ben, some of them are So the question that we are trying to answer in this piece of work is the following, which is what should the role of learning be in the deployment of an autonomous system, right? So we are living in a time in which we hear about machine learning more than we care to hear about, probably. And as persons that care about autonomous systems, we perhaps should be asking what the role of learning should be in the deployment of autonomous systems. If you go and talk with a machine learning person, you will probably get the answer that we should just go ahead and replace our mechanical models with learned models. Because to some extent that has been the big success of machine learning in the last 5 or 6 years, right? In the development of model-free learning algorithms. Now, the point, however, is that models are available, for the problems that we care about, and they are not perfect, but they're not useless either, right? So you could perhaps change that attitude and say that what you would like to do is to learn the mismatch between model and reality. That is certainly fine, but there is still some variability left, right? So particularly when you start talking about heterogeneous things. Therefore, perhaps what you could try and do is to use some sensory input to learn the uncertainty in the execution of your control action. So let me show you an example of what we are trying to say today. So here you have a robot that is making a turn in pavement, that's on the left, and on grass, that's on the right. And the actual trajectory is shown in green in both of these images, and the predicted trajectory is shown in red, right? And those blue things are some uncertainty ellipses that you have around your model trajectories. And what you can obviously see, right, is that these things do not match what your models predicted a priori, and plus, as you probably would have expected, there is more deviation in grass than there is in pavement, essentially because it will skid more than what you expect. Now, so the problem that we would like to tackle, therefore, is the following, right? So, if this is what our models predict, but this is what happens in reality, how can we learn that reality from some sort of sensory input? Okay, so that is, I think, the role that learning should be playing, right? Is the transformation of these, purely model-based navigation trajectories into these learned navigation trajectories that somehow depend on some sensory inputs. Okay, and there are here many ideas that you could pursue. Okay, so the moment you decide that you're going to try and learn those trajectories, then you have an arsenal of learning tools that you could deploy. The one that I will explain specifically is that of task-driven dictionary learning, but we do not think that this is the end of the road. We think that this is just one item out of many that you could consider in this idea of learning. So let me, try to, model this problem mathematically. Okay. So what we have here is, some discrete nonlinear state space equations, right? So we have our state evolution given by some nonlinear function, and that f is what is being given by our mechanical models. But we also have some disturbance g of ak over there, and this disturbance is a function of many things. But in particular, it's a function of the state, and it's a function of some sensory input. Okay, and this sensory input will be, for example, a video feed that you're acquiring from your cameras or whatever. Right? Let's not be specific about that, but generically speaking, you have some state, you have some sensory input, and these two things are grouped into this vector A, and I say that there is some disturbance that depends on those. And this is essentially what we want to learn, right? So the kinematic model, I know it's not exact. We have this mismatch term. This is something, some very classical formulation in robust control. And by the way, right, so if you have some specification for G, you can feed that specification for G into some robust control block, and that would also be a problem that is solved, right? I mean, however, what is not solved is the modeling of this mismatch, right? So in our current state of the art, we have these models in which we incorporate some mismatch. We have these robust control blocks, but we do not have necessarily algorithms to learn the shape or the statistical shape of that mismatch between model and reality. Okay, so let us therefore focus on learning on that, and in order to do that learning, say that you can estimate your state xk, and then therefore you can estimate your uncertainty, right? So this is not something that you have available a priori. This is something that you acquire during deployment, right? So you can compute what your model predicted, you can observe reality, therefore you can compute statistical realizations of your uncertainty, and you want to use these statistical realizations of your uncertainty to learn the statistical model of uncertainty. Okay, so that's a classical machine learning setup, right? So this is this is our model, this is our disturbance. The disturbance has some statistical shape. We don't know the statistical shape, but we can have access to observations of that statistical quantity. We want to learn a statistical model of that statistical quantity. Okay, so if you wish, the architecture that we are incorporating here is this one, right? So this is very classical control. So you have your you have control inputs, you have your outputs. Here you have the environment. What we are adding here is this online dictionary learning block, which is using observations from the outcomes that your control inputs produce, observations from some sensory input, for example, some ground images. You feed those into some online learning dictionary algorithm that will spit this prediction on what you think your uncertainty should be. Okay, so let us look into this dictionary learning piece. So still going into things that are not that interesting. You can, for example, suppose that these disturbances have some Gaussian shape, some mean and variance, and what you want is to study these mean and variances. Right now, these mean and variances, which are the things that now I want to learn. So I have gone from a non-parametric learning problem into a parametric learning problem. These two are still functions of the state and the sensory inputs. This is the quantity A that we have computed before. Okay, and I remind you here that these realizations of pairs A and G, right? These things are available online, right? So you cannot necessarily measure a priori, right? What these disturbances will be. Or actually, if you wish, you can perhaps measure this a priori, but you don't want to, right? You want to deploy the system without having to model. Okay, so how can you write this new hat and sigma hat? Well, you can postulate a linear model for your mean and variance. Right? That's what I will be showing here. So I introduce some regressors W1 and W2, and this is my mean and variance. Now, if you have taken any statistics class, you probably realize, well, you're not telling me actually anything about learning, right? I'm actually telling you about very simple linear regression here, and you would be totally right. This is a little bit of the gall of learning people, I would say. Because the thing that I'm going to change here is the following. So I'm going to say, well, if you have these linear regressors here, it's very unlikely that this thing is a linear regressor, right? I am trying to model these disturbances. I model that as Gaussian. That's not unreasonable because everything is Gaussian. But assuming that these mean and variances are linear functions of your sensory inputs, that's probably very inaccurate. Okay. So instead of doing that, we introduce this dictionary D. Okay, and we say that our mean and variance are linear functions of this dictionary. Okay, and the problem now is a problem not just of simple regression, right? So the regression problem is the determination of W1 and W2, but the real learning problem here is how do we learn this dictionary so that we can have these accurate representations of the distribution that we're trying to learn. Okay? So I repeat then, right? So we started with this uncertainty G that we want to model. This is not complicated. We can model that using this Gaussian model with some unknown mean and covariance. And then we could take the classical regression problem, which is just the computation of this W1 and W2. Okay, but that is not a terribly good idea because it's very unlikely that this linear regression will give you an accurate prediction. But you can say something smarter than that, which is to say, well, yes, I'm still going to do some linear regression, but I will learn a dictionary that will make this representation accurate. Okay? Now, so how do you learn a dictionary that makes these representations accurate? Is perhaps there are different ways of doing that. I am going to describe one way to learn that dictionary. So suppose your dictionary is composed of n basis elements, and you are going to estimate your A's as a linear combination of the dictionary elements. Okay? And you are going to select the projection coefficients that yield a spark calling here. This thing here is called the elastic neck regularization. So you are selecting a projection alpha that makes the actual observations and the dictionary projections close to each other. But you also have this term lambda alpha k here, which is trying to promote the sparsity in the coefficients alpha, meaning you're trying to represent each of the A's using just a few basis coefficients. Okay? So that's how you would solve the projection problem. And then you can formulate this this thing that you could call a generalization of the regression problem, in which you say, well, this is the log likelihood distribution that I would obtain from this Gaussian distribution with means of this form and variance of this form, right? So this is this log likelihood function here. Let me go back, right? So here I have this Gaussian distribution with mu and sigma given through these models, with these alpha stars given through this sparse coding. I put all of that into a log likelihood function. I take the expectation of that over the data set, and I search for the dictionary and the regressors that minimize that log likelihood function. Okay? So in a sense, this is searching for the best linear regressors, W1 and W2 star, but also the best dictionary that will give you those best linear regressors. Okay?
So where do you find the basis elements? You have no?
No, that's a very good question. That's the key, right? I mean, if you know the basis elements, then you just have a linear regression problem. Okay? So the point here is that you do not know these basis elements. So this is the dictionary D, which is composed of these elements, which are part of your optimization space. Okay? So that is, I think, got the question because it means I have not explained properly the key point here, right? So the key point here is that the dictionary elements are not known, okay? So they form part of your optimization space. And what you are searching for is for the dictionary and the regressors that are minimized by expectation. Okay? Now that's a very sensible problem formulation, right? I mean, if we were able to solve this perfectly, meaning if we were able to solve this optimization problem perfectly, then we would be finding the best characterization of our distribution within Gaussian models. Okay? Of course, I mean, this is not possible for a couple of reasons. The first one is that this optimization problem is not convex. The second one is that the objective is an expectation over the data set. Okay, so the way in which you can handle this is that if you look at this optimization problem, you will realize that this problem is convex with respect to D and W1 and W2 separately, right? It's convex in W1 and W2, and it's convex on D, but it's not convex jointly. Now, so that you can handle that using log descent algorithms. The other complicating fact here is that your dictionary, is that your objective is an expectation. You can handle that using stochastic gradient descent. To put all things together, this is how the algorithm would look like here. So you will observe your sensory inputs, CK. You will use the path control inputs to compute this spark coding here. So So this is, this is projecting on the dictionary that you have computed up until this point in time. Right? So I apologize, there is a typo here. This one should be this sub k, and this one should be, and this alpha case should be alpha. Okay, so you are using your dictionary, the dictionary that you already computed to compute the sparse coding. You then utilize that sparse coding that you computed to update the dictionary using a gradient descent step, and then you update your regressors using some gradient descent step as well. So if you go back. If you go back and you look at these gradients, these are not actual gradients, they're stochastic gradients, right? I need to implement gradient descent, I will need to compute gradients of this expectation. Essentially, I remove that expectation. That's why the gradients are called the stochastic gradients. The point is that the stochastic, stochastic gradient descent algorithms are relatively well studied, so it is known that they will converge, and this whole algorithm here will converge dictionaries and regressors that are locally owned. Okay? So the key point in going from here to here are two, right? So the first one is that since the problem is not convex, I resort to block coordinate descent. That doesn't buy me global optimality, but it buys me local optimality. The second key point is that I am removing this expectation with computing gradients. Okay? That is why the gradients are called stochastic, but the stochastic gradients are unbiased estimators of actual gradients, and the algorithms work. Very substantive theory behind it. So that's the algorithm. So we have not tested this in multi-agent systems. So I will just show you what we have done for a simple navigation problem of a single agent. Okay. So here, what we are doing is we are collecting visual patches on the floor, and from these visual patches we compute some signatures that are somewhat known to be able to distinguish, whether this thing is something like pavement or grass. I mean, you can see that this is pavement, you can see that this is grass. So, we compute mean, variance, skewness, kurtosis, we compute some texture, histograms, etc. And all of that gives us some features, right? Some sensory input, as I was calling it before. From that sensory input, CK, we run this algorithm. We compute dictionaries and linear regressors, and then we try to study how much of the uncertainty we have been able to predict. Okay? And what this plot is showing here is the log likelihood that you observe for your actual observations. Okay? So you have estimated the distribution. You say how well my distribution predicts the observations that I am seeing, and you can see that it does, right? So the other things that I am showing here are the common sense things that you would do, right? I mean, you could, this is just you could run things like the Kalman filters or just moving averages. So these are simple benchmarks. The fact is that learning the dictionary works better. Now another thing that is interesting to look at here is the following. So what would happen, right? I mean, if you are trying to train your system in pavement, what happens for the training of grass? Okay, so let me be more explicit here. So here I am switching between navigation in pavement grass, right? And I am showing separately how good the system is at predicting uncertainty in pavement and uncertainty in grass. And this here, these are key moments on this experiment, because what you can see here is the following. So when the robot goes and starts driving into pavement, the uncertainty of your prediction, sorry, not the uncertainty, you say the error on the prediction of the uncertainty starts growing up, okay? Because in a sense, the algorithm is forgetting the fact that it has seen some, it forgets the description of grass, okay? And it focuses on the description of pavement, and that error increases, right? And the same thing happens here. So the system goes again into pavement, we forget the dictionary that describes the grass, and our estimation of grass becomes less reliable. Now, however, what happens, and I could have kept the figure going, but this is where the interesting things stop happening. What happens is that eventually you do learn the difference between grass and pavement, and after learning the difference between grass and pavement, you stop observing that behavior. And this is remarkable because all of this is data-driven, right? So we never told the system that we were switching from grass to pavement. I mean, we just did that and we let the learning algorithm proceed. And what we did observe is, okay, so for a while, the system forgets what it has learned, but eventually the system remembers what it has learned. It actually, we have dictionary elements that are separately describing navigation in grass and navigation in pavement. Yes. This is a similar plot. So this is showing two sigma bounds and actual observations. You can see that they are within each other. And this is just a repeat of the figures that they showed you, right? So, except that now you know what they mean. To close, in the last 30 seconds that I have, is I think that from this exercise we have learned 5 things about what the role of learning should be in heterogeneous teams. The first one is that we should focus on learning uncertainty, because outcomes are random, we can never predict perfectly. The second is that the uncertainty that we should learn is that is left after modeling. We shouldn't be just trying to learn uncertainty from scratch. The third one is, of course, that we want to learn online, right? Because uncertainty will change across time and environments. The fourth one is that we should learn a description of manageable complexity, right? That's why dictionaries are important, is because dictionaries reduce complexity. And then, of course, we should execute control that is robust with respect to the learned uncertainty, right? So 5 is not surprising at all. 1 and 4 are, I think, a little more insightful. And of course, right, we should also learn about collaborative learning in heterogeneous teams, and we have the time to talk about this. That's all I will have.
Very good.
Thank you.